Hello everyone, welcome to this video. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate leaf area index in the Google Earth Engine platform. The LAI is more accurate index compared to NDVI for vegetation density analysis. Now, in the first step, we need to select a study area covered by vegetation, whether it is agricultural area or forest area. For example, I'm gonna select a part of Idaho agricultural fields here. If you go to the satellite view in the northwest of United States, if you zoom in a little bit, easily you can find the Idaho actually here, the Idaho agricultural area, all of them available here. And now you can select a part of this region for the calculation. No matter which area you are selecting, actually this tutorial can be used for all around the world, and you can use it for your own study area because I'm using free satellite data for this tutorial that is available for whole of the world, and you can use it for your own study easily everywhere you want. So there it is. For example, this is a part of area, only we have agricultural fields and also without urban areas or water areas, but there is no problem if there is urbans or water area in your study area, no matter, because thanks to LAI and NDVI and EVI index, we can discriminate vegetation cover from the land and water body and urban area. This is a very simple technique. Using drawing tools available here, I'm gonna select my region of interest. Zoom out a little bit to have a bigger view from our study area, and then I'm gonna select this region like that. Drawing tools is a simple tool available for us, enabling us to select our region of interest using the rectangle tools available here. But I prefer to select a region only covered by the vegetation cover and also without any farmlands actually, without forest or rangeland. But in the other tutorial on my YouTube channel, very soon I will share a video about how to discriminate forest and agricultural regions very easily. So I think this area is better because there are a little poor rangeland here. I'm gonna avoid this region to avoid any problem in the calculations because I only want to have focus on the croplands or farm areas. So if you want to have focus on the study area, it is very simple to use map.center object at first. Here it is, map.center object. I'm going to have focus on the study area that is named as a geometry. Whenever you're running a code, and because of the center object, you will have focus on the geometry that is already drawn here. So now make a new variable as Landsat equals to. Through the search places and dataset, you must go through the indices, you must go through the satellite data you're gonna use. For example, I'm gonna use Landsat 8 and 9, the most updated Landsat missions together for a year, and thanks to coverage or temporal coverage they have, the temporal resolution, when you are using both of them together, the temporal resolution increased to 8 days. That is a good opportunity for the Landsat users to have 30-meter spatial resolution and higher temporal frequency. So through the search places and dataset, type like this, Landsat 8 collection 2 level 2. Just a moment, and after a few moments you can see the Landsat 8 collection 2 level 2. This part is a little tricky and sometimes needs some sort of change in the name to see the level 8 collection 2 level 2. As you can see, these data are already corrected geometrically, atmospherically, and radiometrically. And this is a good product to calculate spectral indices, whether it is for vegetation cover, urban areas, or the other land covers on the Earth's surface. import it into the code like this, and now we will have a new image collection belongs to Landsat 8. So if you want to do the same for the Landsat 9, here just you must go to the search places and dataset and type about or find Landsat 9 collection to level 2 data, and then import it as the second image collection. So if you go to the data description, you can see the Landsat 9 data available since October 2021, and the Landsat 8 data is available since 2013, meaning that after 2021 or 2022, we can use Landsat 8 and 9 together. So now back to the code. If you want to have these Landsats together under a single variable, it is very easy. You must type image collection first, the Landsat 8 dot merge. I'm gonna merging two collections because I want to have a single collection including Landsat 8 and Landsat 9, and this is a good opportunity because both of them carries LAI sensors with the same bands, characteristic, and spectral characteristic, and temporal, and also the spatial resolution. That is a good opportunity for us to combine Landsat 8 and 9 together after 2028, after 2022. That highly increases the accuracy of Landsat estimations, specifically from temporal point of view. So here I'm merging with Landsat 9. Here it is, the second image collection. So if you press on tab a little bit, you can come a little further and then sort the data based on system time start. It is very important because we are combining or merging two different collections, two separate collections into a single one, and it is very important to sort all the data according to date acquisition, and because for the time series analysis, it is very important to have all data in a right order from temporal point of view. So now I'm gonna have two variables. The first is the time start. I'm gonna call those Landsat data starts from 2023 to 2024. Start date or time start will be 24, and time end equals to Earth engine. That's date. Sorry, the start date should be 23, and end will be 24, just like that. Then define your data according to the time start, or filter your data according to the time start and time end. Then next, you must filter your data based on the region of interest, that is geometry. I'm gonna have all Landsat 8 and 9 images that is sorted based on date acquisition, and that is limited to 2023 for the regions I have selected, a part of Idaho agricultural area. So there it is. So for the next step, I want to see how many Landsat data available for this period of time. Print Landsat. After a few moments in the right panel, you will see a problem. There is a problem here. Yes, I must use filter date here instead of filter bounds. Filter bounds works with geometry, but the filter date we must have to define the time start and time end. Write the code again. In the right panel, as you can see, 159 images available since the start of 2023 to the end of 2023 or early 2024. So what is the next step? In the next step, I'm going to show you how to calculate the NDVI, EVI, and finally LAI or leaf area index. So now I'm gonna make a new variable as vegetation, as LAI, for example. LAI equals to, now I'm gonna bring Landsat data first here, all 159 data, and make a loop to do calculation for the rest of the data. As you can see, we have 159 data for 2023 over this region, and it is very important for us to calculate NDVI, EVI, and LAI for each one of them separately. To do this, to make a loop, I need to use .map here. Then we will have a function inside that allows to do some sort of calculations on each image separately. Now I'm gonna have each imported data into a function as an IMG, and then before go through the spectral indices, we need to prepare our data. As I mentioned earlier, the Landsat collection tool level 2 is already corrected radiometrically and atmospherically, but there are some coefficients that suggested by the NASA, USGS, and Google Earth Engine that should be applied on the data before, and then we can go through these indices. First, I'm gonna have a variable as bands in which I can select the target bands here. From each input image, I'm gonna select the target band. What the target band is, if you go to the data description, no matter it is Landsat 8 and 9, because both of them has same spectral characteristic. Here, you will see that after a few moments, if you go to the bands, here you can see surface reflectance bands available from band 1 to band 7. These are the main bands we need to calculate NDVI or other spectral indices related to the vegetation cover, at least for this study. So I'm gonna select all the bands starting with SR, and the rest of them is no matter. Back to the code here, and if you want to have multi-spectral band, you must select all the bands starting with SRB, and the rest of that is no matter. So then there is a coefficient as a scale and factor that you can see. This is the same in all the bands. It is like a linear equation. Each one of the bands must be applied to and must be multiplied to the scale, and then will be added to the offset value. It is a kind of linear equation that should be applied on integer data or digital number data first to convert it from digital number to the surface reflectance value. At least for the spectral index analysis, if you have access to the correct coefficients values, such as the scale and factor we have here, it is necessary to apply them before any analysis. For the spectral related, I mean. So the scale value was like that. Just copy and paste it into the code. Dot multiply and then dot add. If you go to the data description, dot add is minus 0.2. So now the bands selected and actually the coefficients applied on each data. Now we can calculate the NDVI. The NDVI equals to bands dot normalized difference vegetation index. Actually, the normalized difference is a kind of function in the Earth Engine allows to users to calculate normalization relationship between two input bands. For example, I'm gonna get normalization relationship between SR band 5 as a near infrared band and SR band 4 as a red band. There it is. And then rename it to NDVI, just like that. And function should return one or couple of results here. For now, I'm gonna return the NDVI with the properties of input images. But property, what does it mean about the property? As you can see, for each image, there are some bands and also properties. The property is something like metadata that's covering lots of information about the data characteristic, cloud cover, data acquisition, and also coefficients, necessary coefficients, and etc. But for this tutorial, the only properties should consider is time start and time end, because I'm gonna do some sort of very simple time series to show you how NDVI, EVI, or even LAI changing during the time. IMG, and now here from input properties, just I need system time start and system time end, just like that. print LAI and run a code. Remember to save your code to avoid any issues related to the code. So here, as you can see, here the NDVI calculated for all the bands. But the question is how we can calculate the LAI, because we know that the LAI is much accurate than NDVI, because when vegetation grows a lot and also when we have a full cover vegetation, NDVI cannot discriminate vegetation covers easily, or it is saturated in other way. So that's why we need to use LAI, because it is more accurate to discriminate the vegetation cover when most of the vegetation covers reach to the peak. So that's why I'm gonna introduce you one reference. This is my reference for Landsat Leaf Area Index. That you can see there is a reference for this index, and also I'm picking this reference from mv5geospatialsoftware.com. These are the reference I'm using for this tutorial for the LAI equation. Although this is the equation that MV software users use, but now we can write this equation easily in the Google Earth Engine platform. That's why I'm always suggesting to use coding and a scripting technique, because you can do anything that you want, and if there is not something there, you can calculate by your own skills. So as you can see, this is the equation, and one necessary term here is enhanced vegetation index. The enhanced vegetation index, if you click on it, you will go to a new page, and here enhanced vegetation index, that is a kind of a spectral index for vegetation cover analysis that's useful for the greenness analysis, and also, as you can see, a scattering or atmospheric impact also optimized or reduced or adjusted by some correction terms in the denominator part. So, and also this is a index, this is also a reference for EVI index. I'm using these equations to calculate the LAI. So as you can see, the first we need to calculate the EVI. Already Landsat data bringing, and now we want to calculate the EVI first. So back to the code now. This is the sample code I had before, and this is the code I was working here. So now I'm gonna calculate the EVI, enhanced vegetation index, equals to, from the input bands, I'm gonna, using the input bands, I'm gonna write an expression. The expression is another kind of function for calculations that help us to write own equation. In the normalized difference, you only limit it to the normalized structure. Two parameters, one of them minus another one, over to actually one of them add to another one. But in the expression, you can write anything, all the equations you are thinking. So it is something like band mass in the NV, ArcGIS, or Snap software, or QGIS, something like band calculator. You are easily write your own idea from the equation point of view. So here we need to have two. Here there is a division process. We have two sides. One side numerator and another side denominator. If you go to the reference here, this is for NDVI. In the numerator, you will have a subtraction between near infrared and red. Back to the code. Here in the left side, near infrared minus red. Same as the reference we have. And also in the denominator, the other side, we have NIR plus 6, NIR plus 6, multiply, go to the reference again, multiply red minus 7.5, red minus 7.5. So here 7.5, multiply blue plus 1. Multiply blue plus 1. There is an equation. This is an expression we're going to use for the EVI. So And if you back to the reference, you can see there is a coefficient that multiplied to the whole of the division process. 2.5 multiplied to all sides, left or right. And here I'm putting all the division into a single parenthesis and then type 2.5 multiply to the whole of division process. So the equation is written, and now we need to define known variable instead of unknown variables we already mentioned in the equation here. So, for example, we set NIR as an unknown variable. From input bands, I'm gonna introduce band SR, band number 5 as near infrared. And then we have red. From input bands, I'm gonna select SR band number 4. There it is. And the next one is blue band. Blue equals to, from input bands, I'm gonna select band number 2. As you know, band number 2 and number 1, both of them covers blue region of electromagnetic spectrum, but most of the time, typically, band number 2 use in the indices unless it is mentioned that you have to use band number 1. So now I'm renaming it as EVI just like that. So after EVI calculated, we can have it as a separate band next to the NDVI in a stack layer. So now EVI is calculated and added to the NDVI or existing NDVI. Back to the reference, and here you can see after EVI calculated, you can have you can calculate the LAI by two constant value that mentioned here. LAI equals to this relationship, and this value multiply to EVI minus to another value. So it is very simple technique. Just make a new expression for the LAI equals to, now the input band here is the EVI. That's why instead of bands, now I should write EVI dot expression, because I'm gonna write the expression based on an EVI. So the EVI, the first value is, let me to check it now, 3.618. 3.618 multiply to EVI minus 0.0118, I think. Let's check it again. Here, 0.118. One extra zero should remove here. And now the unknown parameter is EVI equals to EVI.select EVI. There it is. So LAI also calculated. Now add bands for LAI. LAI, NDVI, and EVI, all of them calculated. Remember to save your code and run it again. If there is any syntax error here, as you can see, you will face with the error. Most of the time, if you read the error, you understand what the problem is or what the source of problem. For example, here mentioned that band pattern B2 didn't match to any bands. If you go to the band selection here, you can see that the blue bands selected as B2, that is a wrong name. You should write it as SRB2. So the problem is solved, and now for each date, you will have three bands, NDVI, EVI, and also a constant value. So the LAI name should rename, the LAI output should be renamed as LAI. Run the code and save your code. In the right panel, you can see you will have EVI and LAI next to the NDVI values. So now in the next step, I'm going to show you how to mosaic your study area, because definitely your study area covered by different images from different paths and rows. And it is very important to mosaic images for every 8 days to cover your study area completely. It is very, very important things in when you are working with the data such as Landsat that follows framing structure. Most of the time your area is covered by multi-frames, and you need to do some sort of mosaicing process to see whole of your study area in a single frame for each day. So now I'm gonna, before that, I'm gonna do a visualization using map.add-layer. Here it is the LAI image, and I'm gonna actually just call the first, for example, 20 images from 159 data, and then make a stack layer using .2 bands that is clipped based on the region of interest, just like that, to see how much of the area cover in this region, how much of the study area covered by different frames. So leave the visualization parameters empty and turn its name to the LAI or vegetation indices, no matter, whatever you want. And also put the false at the end that helps you to avoid automatic visualization. Let's save your code again and run it again. You will have focus on the study area and once the data calculated. If you go to the data description, you can see the NDVI, LAI, and EVI calculated for different dates. For example, this is an LAI, one of them selected, and then I'm gonna increase the contrast by 90%, but remember to check it on to see the whole region of interest. As you can see, for this date, for example, a region, our study area is covered by, maybe it's covered by cloud cover. Let me try the other techniques for increasing the contrast. Yes, it seems covered by cloud or other things. Let me just select a period that is less covered by the cloud, or we can have here a filter for the cloud cover, Earth engine.filter.lt. I'm gonna use those data in which cloud cover is less than, for example, 10%. Only cloud-free data called here. We have 53 data, and check it on, and you can see that, for example, one of the images only covering a part of your study area. That's the situation we have. I wanted to show you this. And then go for the LAI again. Yes, in this image, as you can see, we have the LAI image, but in this frame, the area is covered by the our region of interest already covered by this frame, but maybe in another frame only a part of it covered by the satellite data. So as you can see, in this image only a part of that is covered by the image, and also a part of information is missed. Now I'm gonna show you how you can make a mosaic according to the maximum value composite technique in the Google Earth Engine platform. That is very helpful technique to mosaic and reduce the cloud impact in the satellite data, specifically for the NDVI and vegetation indices. So in the first step, I'm gonna actually calculate the temporal differences between time end and time start. Now I'm gonna do mosaicing process for every 8 days. That's why I need to calculate first the temporal differences between time start and time end, how many days we have between. Here it is, the time difference equals to from time end dot difference. I'm gonna calculate the difference until time start according to day units. If you print time difference, most likely you will see 365 days we have from time start and time end. Now I'm gonna make a list of dates from first to the end day of 23 that with 8 days interval, because when you are using Landsat 8 and 9 together, in that case, you will have higher temporal frequency instead of, for example, 16 days, you will have access to data with 8 days temporal frequency. That is awesome for such kind of studies or agricultural monitoring. So that's why I'm gonna make a list of the dates first, Earth Engine, that's list, that sequence. It is a very, very simple technique, and also don't afraid to write the codes or write something a little complex. Try to do it and practice by your own. That is helping you to increase your knowledge or increase your information and skills in working with codes and function in the Earth Engine platform. So Earth Engine, that's list here, a couple of arguments we have. The data started from day 0 and ends to the end date or 300 time difference. So I'm gonna have a list starting from 0 to time difference value, that is 365. But as you can see, I'm starting from 0 and time difference is 365. In this case, I will have 366 because I'm starting from 0. So I need to make a little subtraction here. I'm gonna subtract it from 1 to have 365 elements at the end. So the step is very important. So as we wanna have 8 days temporal, the step should be 8 here. And we skip the count first. And now, as you can see, we have a list starting with 0 with 8 intervals until the end of year. So there it is. Now I'm gonna replace the numbers with the dates. It's very simple technique. Just make a map, make a loop first using map. Whenever you want to make a loop, map is used in the Google Earth Engine. And now I'm gonna do some sort of calculation inside the map. That's why I need a function. The input actually value or input number are delta value. Delta or just only the numbers. No matter, you can choose any other name. So the function returning for each number or instead of each number, Earth Engine dot date dot from YMD, from YMD. So couple of arguments. The year is equal to 2023, month equal to 1, and date also equal to 1 because our data is starting from January 23. And then I'm gonna go advance like this. I'm gonna go forward using advance from origin with numbers delay. Actually, the 8 days. The numbers carry the difference or explaining the delta time starting from origin based on units, the unit measurement, that is days. So now if you run a code again you will have a list with 46 elements, but this time instead of numbers you will have a starting date with 8 days interval starting from January and ends to the December 23. So there it is. Now the list of a starting date is ready, and now I need to write a code to define the end date and then filter my data according to the new start and new end date, and then make a mosaic using maximum technique. So just make a new function here, make a new variable here. The new variable is, for example, the mosaic data equals to first define an image collection structure and bring the list inside the image collection structure, because finally we're supposed to have a collection as an output. So we don't we don't want to have a list at the end. The list helps us to do the calculation. It's a framework for calculation, but finally we want to have it as an image collection format. So inside the image collection, bring the list just here and make a loop to do some sort of calculation for each starting date that we have inside the list. Make a new function to do the calculation. So now in the list we have the start date, or just we have the dates that could be a start date. The next part inside the body, the start date equals to date equals the date. The start date already defined. So now I'm gonna have the end date here. End date equals to, so from start date go forward using advance according to a delta. This is the 8. We can set a delta here as interval, make a variable as interval here. For example, our interval is 8. We want to have the mosaic data for each 8 days, and then replace the 8 with interval value. So the unit is days, and remove the time zone just like that. So start date and end date calculated, and now we want to do mosaic process IMG. The IMG including the LAI, NDVI, and also the EVI, NDVI, and LAI, all of them together. But it is better to turn the LAI name, it is better to avoid a repeat of the same name inside the code. For example, here I already had LAI, now I can turn it into an index to avoid actually redundancy in the name, because sometimes cause some sort of problems during processing the steps. The IMG equals to, I'm gonna have all indices that is filtered based on a start date and end date. Start date and end date here I have, and I'm gonna get maximum value in each image for each pixel separately. Just like that, the maximum value calculated here, and no need to rename it to a new name, just return the IMG. When you are getting the maximum value for each image for each 8 days, meaning that you are collecting all available images for each 8 days and then merging into each other or aggregating them using maximum operator, so that the maximum value in each pixel calculated. So the finally image returning with a new system time start and new system time end. As now we have 8 days data, so we need to have a new system time start and new system time end. That's set system time start equals to start date, but should return it, convert it to the millisecond format. Again, that's set as system time end, just like that, end date, that's millisecond format. And if you want to have a new system index, you should write system index. Let me to remove some mistakes here. System index. System index equals to start date dot date. So sorry, dot format. I'm gonna have a start date as a string with this format: years, month, and day, just like that. So let's print the final result. Print mosaic image in the right panel. So the LAI is not defined here. It is not LAI anymore. This is index. So LAI is not defined again. There is a problem here. So the index is wrong. In the right panel, as you can see, 46 element is available, and also the NDVI is calculated for each 8 days. But since for some of the dates we didn't have actually enough data to collect them, to aggregate them, into a single image as a mosaic data. So that's why some of the dates already included 0 bands. So now we can increase the temporal frequency from 8 to 10. In that case, we will have more data, 35 elements we have, but I think something is wrong here. Let me to check it first. Now I made a Landsat. This is the index. This is for visualization. We are starting from 0 to and here. Yeah, the problem is about the cloud cover, and now you should remove the cloud cover from the code. If you run a code in the right panel, you will have 35 elements. So as you can see here, only 2 dates data is for the 2 days the data are missing. But let's try for the 8 days interval again, because the cloud cover filter is just removed. And in the right panel, you can see 46 elements here we have, but still 2 of the dates or 2 of the elements, including 0 images. So there is a way to get rid of these actually missed data in the 4th element and also 35 element or element number 35. There is a very simple technique that we can filter the data based on number of the bands. For example, here I can make a variable as band size equals to, from each input image, I'm gonna get the name of each band, and then I'm gonna calculate the number of the bands according to their name. So here, now we need to set a new property as a band size. The band size equals to the band size. No need to add equal sign. That's band size like this. And then if you run a code in the right panel, still we have 46 data, but for each date we have a band size as 3. But for the day with 0 band or for the date with 0 band, the band size is 0. Now I can define a filter, a greater than filter, to filter my data based on number of the bands easily. We'll make a filter, earthengine.filter.gt. I'm gonna filter the data, and I'm gonna have those of images in which band size is greater than 0. So run a code, and then in the right panel you will have 44 images, and also there is no problem there. So next I'm gonna do visualization for the LAI band using map.addLayer. So as you can see, couple of arguments we have here. The input object is mosaic data using maximum value composite technique. Through the select, I'm gonna select the target band that is LAI, then make a stack layer that allows you to select different dates, and then clip it based on the region of interest that is geometry here. So leave the visualization parameters empty and change the name to the LAI, and then turn the shown to the false because we want to avoid automatic visualization. So just save your code and run it again. As you can see here, we have new layers as LAI that you can see LAI for different dates. For example, I'm gonna select one of them and then increase its contrast by 90% of value and turn it on. And now as you can see, the calculated LAI for the region of interest is shown here. Unfortunately, part of this area is still covered by the cloud. That totally makes sense. And so in that case, if you want to get rid of the cloud, you must actually reduce you must add the cloud filter again, and also increase the number of interval to able to make actually the mosaic data for a longer period of time. So Now I'm gonna select another date, for example, from the summertime. And as you can see, the LAI value ranges from 0 to 4 or 5. That changes and depends on the density of vegetation you have in the region of interest. A higher vegetation cover, higher LAI value, and vice versa. So I'm gonna try this for June, June 2nd, 23. So as you can see, this is LAI that shows where we have higher vegetation cover and where we have lower vegetation cover. Okay. And now I'm gonna select the part of that region to see how LAI value changes during the time. For example, I'm gonna pick a value from a region. For example, here I'm gonna mark a point here using drawing tools for the second geometry, not the previous one. I'm selecting, for example, this area. Just a point is marked here, and I'm gonna see that how the LAI values changes on this point. So map.center object, here we need to print a chart. Print user interface chart dot image dot series. As you can see, instead of image collection, you must have your mosaic image. The region is geometry number 2. As it is a marked region, you need to get the first value, Earth engine.reducer.first, just like that. And now the scale should be 30 because of the spatial resolution, and X property equals to system time start, just like that. Run a code and see how the value changes during a time. So a couple of bands here we have, but I'm suggesting you to select the target band, that is the LAI. I'm gonna select the LAI value, just like that, but this is not capital. And now in the right panel, you can see the NDWI variation during the time. Some of the negative values definitely occur because of the cloud cover, but you can remove these states. And also we have some values above and around, and here maybe there are some noises in the temporal period. But in another way, you can also select the growing season period. For example, in these states, in the March, for example, we know that there were no vegetation cover here, but as you can see, starting from May, June, July, the LAI increased and then reduced. So we can also limit our data to the period of time, that calendar range in which crop is growing. The filter Earth engine that filter that calendar range. So starting from, for example, month 5, May, and ends to, for example, October, and the field is months here. Run the code again. Then in the right panel, as you can see, this is a true range of values or variations that you can see or you can expect from the LAI during the time. So now we can have the same chart, this time for the NDVI. So in the right panel, you will have a new chart next to the previous one that shows the LAI NDVI variation. Both of them are closely matched together, but NDVI is LAI is more accurate in actually very high density situation, and also they have also a little differences. But if you want to study about the density of the vegetation, definitely the LAI works much better than the NDVI, because it's not gonna be saturated in the high level, high density vegetation cover. So, and that was the tutorial about LAI calculation in the Google Earth Engine platform. And now if you want to get export from the LAI during the growing season, just you must use export that image to drive, just like that. The image you want to get export equals to the LAI image for the growing season that is already filtered. And then I'm gonna make a stack layer using .to bands, and the next is the description. Name of output layer is the LAI. The scale of output should be equal to 30-meter spatial resolution. Region of interest equals to geometry number 2. And also the CRS coordinate system equals to EPSG E4326. This is a code that we use for WGS84 coordinate system for all around the world. So the next parameter is necessary here is a folder you want to get export in, and also it could be test or any other folder you prefer in your Google Drive. And the next one, maximum pixel load for the export equals to 1E13 for each frame. We will get an export from Earth Engine, and these are the things that you should consider for export process. But if your area of interest is very big, definitely you will face with a lot of problem for getting export. I'm suggesting you to reduce the area or reduce the spatial resolution or pixel size through the scale value, for example, to 100. And then save your code and run it again. In the right panel, under task here, you will see a new task as a LAI. It is ready to save. If you click on run and again on run, the process of saving starts, and then the process will be done until the tab color turns to the blue one, like the before test I have here, and then you can pick it up from the Google Drive. I hope you like this tutorial as much as I did, and I hope you can use this tutorial for your studies. And if you had any questions or any problem, feel free to reach me out on YouTube channel. And I'm really appreciated for your attention and asking you to share this video with your audience or community that you are working with. Thank you for the attention again.